Hello, welcome back. I hope the first two videos, well, they're both part of the same question, kind of helped you relax a little bit about what the class is about. Recall that what we really care about, what's going on inside the material, how and why the material is doing what it's doing, and what's really causing it to do what it's doing. All right, so we talked about stress and how we look at internal forces. So for the first video, what we really cared about was your shear and axial forces, only that kind of affecting the material to be able to find your stress. Now we're going to look at strain. Now strain is just simply any kind of deformation and how some kind of force changes the body of any kind of material or structure that you have. Now for normal strain, if an axial load is applied to that bar, basically under axial load, you're going to change from L naught, which is basically your initial knot, L, sorry, your initial length, to L, which is basically your final length. All right, so average normal strain, and this equation is important because we're going to use it over and over, is your final length minus your initial length over the initial length. Or we can say you have your delta L over L naught. Simple as that. That's basically it. All right. So example, if your initial diameter was 6 inches and then your final diameter was 7 inches, what is average normal stress? Simple, right? And we've just talked about this. What you have to do is just simply 7 inches minus 6 inches over 6 inches, which gives us 0.167 inch per inch. And that's our final answer. That's as simple as that. It's pretty nice, right? All right, let's do a little bit more challenging question. So if you look at problem 2.3 from the book, simple as if we have, and I'm going to try to use the same system as we used before. So another example, we have a beam, okay? And then we have some tension loads on it. So we have some tension right here. And then we also have some tension right here. We're just going to call this TBD. And we're going to call this TCE. So base tension can be from a rope or some kind of thread that's really trying to force the beam to not fall down. Now, this beam on this side is supported by a pin, which is why we need the tension on the two sides so it doesn't rotate and become unstable. So we have AX and AY. And then we also have a concentrated load right here. Okay? And then our dimension, which is very important, especially in this case, this is 3 meters, 2 meters, and 2 meters. Now, don't forget, and this is important, I cannot draw. I can't draw a straight line to save my life. So if everything is all crooked, it doesn't mean I don't care. I really do care, and I try really hard to make it look pretty, just not going to be as pretty. But in your homework assignments, I expect to see very beautiful lines drawn, and you will see that in all handwritten solutions as well. So keep that in mind. All right, so the question here is that if this end is NC, okay, going back to my black pen, if this end is NC, NC is displaced 10 millimeters downward. And then we are saying that find the normal strain in wires CE and BD. Now, let's think about it for a second. Why is there normal strain? Apologize for that, that's just my email. Why is there normal strain in BD, wire BD, which is what's causing the strain in tension BD, and then CE? So because of the point load P pushing down on the beam AC, it's going to want to go downward because, for example, on the left hand side at point A, we have a pin, which means that it's going to want to rotate because it doesn't support any moment, right? So what's going to happen is our BD and CE wires are going to want to stretch just to be able to accommodate that. Now, what we're going to do is we're going to draw, where's my explanation pen, which is this color. We're going to draw the displacement profile of member A, B, C. Okay, so this is point B. So if you're drawing the displacement profile, sorry about that, I'm going to go back to my black pen. Okay, I guess the trick is a little bit of confidence. That's really it. And we're going to see that our beam, so A, B, D, A, B is somewhere here, and then D is BC, sorry, BC is somewhere here. So remember that this is 3 meters, and this is basically about 4 meters. So if we are saying that our beam is going to displace downward 10 millimeters, we can also call that our change in length of EC. So our wire EC is going to stretch. Okay, and that delta is 10 millimeters. Okay, so then what we need to know is what's going to happen to BD. So delta BD is going to something that we don't know. So we're going to use proportional triangles, and we're going to say that delta BD over this distance, 3 meters, is equal to delta EC over 7 meters. So this 10 meters is over the entire 10 millimeters over the entire 7 meters, but this delta BD is only over 3 millimeters, which means that our delta BD, which we don't know, is equal to 10 millimeters times 3 meters over 7 meters. So our delta BD is equal to 4.286 millimeters. All right, so the next step, which is basically our last step, is we want to know the strains, okay? So strain in CE, which is at the end, right, from TCE, is equal to delta LCE over LCE. Now this can also be known as delta CE over LCE. Now original length of our delta right here, so original length of our wire, so length of each wire is equal to 4 meters. So coming back down here, we'll see that CE is 10 millimeters over 4 meters. That means that delta CE is equal to 0.0025 millimeters per millimeter. And then our delta, what's the other one? BD is equal to delta BD over LBD, which is 4.286 millimeters over 4 meters. Now delta BD is equal to 0.00107 millimeter per millimeter. And it's as simple as that. Okay, so to recap, in this problem, we really did not care about any kind of support reaction or external loads, but what the external loads are doing to the beam. And we are given that very simply over there that NC was displaced 10 millimeter downward, which just gives us everything that we need to know to be able to find out strains. So recap, remember that our normal strain is just a delta or a change in length or distance or diameter or area or anything divided by the original length or diameter or area or anything. All right, so I hope these two videos kind of help you out. Thank you.